Okay, welcome everybody. It's really great to see so many of you joining us this afternoon. So welcome to the next instalment of our online RAS ordinary meeting. It's going to be a really good one. We have two fantastic speakers this afternoon. So as always, just a little bit of housekeeping before we start. This meeting is taking place via a webinar. If you look at the top left of your screen, hopefully you should see a small green shield, and that symbol means that you're using the most up-to-date version of Zoom and that it is secure. And I do also need to advise you that this meeting is being recorded. Now, after each presentation, as always, you can ask questions, but because you will be muted, don't forget to use the chat facility to ask those questions, which can be found at the bottom of your screen. Your questions will come to the panelists only, and they will be read out and facilitated by our editorial team member, Dr. Louise Alexander. Okay, so I just have one important deadline announcement before we get started, and that relates to elections to Ras Council. So may I just please remind you to propose a colleague or indeed to put yourself forward for election to Ras Council, and the deadline for nominations for that is Friday, the 26th of November, 2021. Okay, so we're going to move now on to our programme. So we have two speakers this afternoon, and I'm really pleased to introduce our first speaker, Dr. Alexandra Amon. So after growing up in Trinidad and Tobago, Dr. Alexandra Amon studied at the University of Edinburgh and then was a Kavli Fellow at Stanford University before moving to Cambridge University, where she is now a Senior Kavli Fellow. So Dr. Amon's research focuses on cosmology and our understanding of the dark universe using a tool called weak gravitational lensing. And at present, she coordinates the lensing team from the Dark Energy Survey, which is a large international collaboration. I'm sure we'll hear more about that in her presentation. Her doctoral thesis, titled Cosmology with the Kilo-Degree Lensing Survey, won the Royal Astronomical Society Michael Penston Thesis Prize in 2018. So I'm really delighted to now hand over to Dr. Alexandra Amon, who is going to be talking about shedding light on the dark universe with weak lensing. Over to you, Alexandra. Thank you very much.
Thanks, Emma. Let me make sure I can share screen properly. And hopefully you all should see my screen, the full screen.
Yes, that looks great. Thank you.
Great. Okay. So thank you so much to the RAS for this prize that shines a light on scientists that are coming fresh out of their PhD. I'm delighted to be able to finally give you this talk and pleasantly surprised to see so many of you online. Because it's a few years late, you'll see what looks like a little bit of institution confusion at the top of my slide. So as Emma was saying, I did my PhD, which this prize is for, at the University of Edinburgh with the fantastic Professor Catherine Haymans as an advisor, and she is now Astronomer Royal for Scotland. And I was very lucky to have such an expert advisor, not just to teach me about the field, but also to show me a whole new career path that I didn't know existed. And then the work that I am going to talk about today was mainly done at Stanford University, so I just thought I should include that one. And finally, I'm now happily back in the UK as a senior fellow at Cambridge. So that explains the three of them. Now tonight, in just 20 minutes, I will start by telling you where our field of cosmology is at right now in our pursuit to answer some of the big questions. So what our universe is made of and how did it evolve to the way that we see it today. Next, I'll explain weak lensing and the surveys that are on Sky right now, and a bit about the process of how we make our measurements and use them to constrain our cosmological model. And then in particular, I'll tell you about the Dark Energy Survey Year 3 analysis, which we released earlier this year and was an analysis that I led. And finally, I'll end with about how the field might move forward given the results that I'm about to show. So starting with what we know, this is the picture of our universe's story as we understand it. So 13.8 billion years ago, the early universe was this hot, dense soup of particles with very tiny density fluctuations governed by quantum physics. Now, then the universe went under this period of rapid expansion called inflation, which left an imprint of the fluctuations at that time. And we call this the first light of the universe, or the cosmic microwave background, or the CMB for short. And you can measure it as a map of the fluctuations in temperature and in density from the early universe. So a snippet of that map as measured by the Planck satellite is shown in the bottom left there. Now, the expansion of the universe marched on, and those fluctuations cooled and expanded such that they seeded the large-scale structure in the universe that we observe today. So the parts of that soup that were most dense formed the first clumps of particles, eventually the first stars and galaxies, and today perhaps the biggest galaxy clusters. And so that random pattern in the cosmic microwave background is responsible for the pattern in the large-scale structure that we observe in our cosmic web today. Now, what else do we know in our picture? We know that when we zoom out enough, the universe looks like this cosmic web. So there are dark matter clusters and filaments that form the bones of the universe upon which galaxies live, and stable dark matter halos that extend far beyond the visible light of the galaxies that live within it. And dark matter is crucial to the formation of structure that we observe in our universe. It does the job of gluing galaxies together. And so without it, we wouldn't have the same structure that we observe today. Now, we also know initially, thanks to supernova observations in 1998, that the universe is expanding, and that expansion is getting faster and faster every day. So an accelerated expansion. And we attribute this phenomenon to dark energy, which is associated with a cosmological constant in Einstein's equations. Now, if we go back to this picture, we can write down a pretty simple model for our universe, and we call that model lambda CDM, lambda for dark energy and CDM for cold dark matter. And this model holds up pretty remarkably to whatever cosmological observations we seem to throw at it. So whether we're talking about observations of supernova to constrain the distance ladder, or to those microwave observations of the CMB, or to large-scale structure observations that measure the clustering and the lensing of galaxies. And it is impressive that such a diverse set of observations can be described by this model. Now, on the other hand, it's pretty deeply unsettling that at the foundation of this model are dark matter and dark energy, comprising of most of the stuff in the universe, and they are entities that, of course, we don't really understand. Now, measurements of large-scale structure measure the late-time universe. So tried to indicate that with this purple box. So they probe the current era that's dominated by dark energy. And so they're really important for shaping this cosmological model. On the other hand, measurements of the cosmic microwave background probe the universe as it was 13.8 billion years ago. So they measure the imprint of those very tiny density fluctuations when the early universe was just that soup of particles, so well before the onset of galaxies and an accelerating universe and a domination by dark energy. So you can see already that those, when we compare these observations, we create quite a beautiful end-to-end test. So those CMB measurements made by the Planck team are the gold standard experiment of our field. They fit our standard model of cosmology to exquisite precision. But we want to know, can we use that same picture that fits the seeds of our universe to describe the vast structures that formed billions of years later? And really, that's where weak gravitational lensing comes in and has a lot of power to play. Now, how does lensing work? So the presence of foreground massive objects like these gray blobs here distorts the fabric of the universe, that orange grid, so that as light journeys across the universe from even further away background galaxies, its light path gets bent due to these distortions. The path of the light gets bent. Now that means that every image that we take is slightly distorted with the imprint of the cosmos between us and that galaxy, and we call these distortions shares. These galaxies, that we observe them to be lensed, and they have a share. Now, galaxies whose light travel past the same structures in the universe, like these two galaxies on the bottom left here, acquire coherent distortions and alignments. So they are lensed, and we would measure a correlation between their shares. Now we can think about this on a cosmological scale now. If you consider the simulation box on the top right here, the yellow toy galaxies live in the back of the box, or further away. And the statistical measurements of the observed shares in that image plane at the front would show correlations. So that these measurements tell us about the matter distribution that the light traveled through. So the matter distribution in the box. So weak lensing tells us about all the stuff in the universe that the light traveled by. Now, to do weak lensing, we need, from our toy yellow galaxies here, we need their positions and a measure of the shapes of the galaxies. And we quantify these shapes in terms of an ellipticity that's two components, E1 and E2. And with these shapes, we can compute we call them the correlation functions, the share 2-point correlation functions between pairs of shapes separated by some angular radius theta. So I tried to indicate that in the bottom right there. So psi plus and psi minus are our measurements, and we measure them as a function of theta. So higher psi plus and psi minus means there was more lensing or more stuff or clumpy stuff that the universe passed through. Now, to model our signal, we need to understand how far away the galaxies in our sample are. So we don't have distances for every single galaxy that are very precise or that are very accurate, called redshifts. But we measure the redshift distribution of our galaxies. Now, to maximally extract the information from our surveys, from our data, we do our analysis tomographically, we call it, which just means we take that box, that volume that we've observed, so the black box, all of the data that we've observed, and we slice it up into bins of distance away from us, or redshift. So in this example here, we have 4 redshift bins. And in reality, we're not measuring the correlation functions of not of the entire sample, but of pairs of galaxies within each bin and across bins. Now, the correlation functions that we measure are directly related to the underlying structure of the universe, and that's what's key here. They are the amount of correlation that we observe, or the amount of lensing that we observe, is particularly sensitive to omega matter, the amount of matter in our universe, one of our cosmological parameters, and sigma 8, which is the amount of structure or the clumpiness of that matter. And so often lensing analyses or lensing surveys, we quantify this S8 parameter shown here, which is just telling you about the amount and the clumpiness of structure in our universe. And you'll see this parameter come up a lot, because this is what lensing is most sensitive to. So it's the parameter that we constrain best in our cosmological model. Now, doing our analysis in these redshift bins allows us to look at how structure evolved with redshift, or going back in time. And so it lets us understand how our model is working as a function of time, and therefore let us understand dark energy. Now, the largest lensing data set on the market right now comes from the Dark Energy Survey. And I've spent most of my time in the US working on this very beautiful data, and now coordinates the main lensing team. So DES, the Dark Energy Survey, is a 6-year survey, and we've now completed observations. They were taken from the Blanco Telescope on the top of Cerro Tololo Mountain in Chile. And the survey spans 5,000 square degrees on the sky. So that's 1/8 of our night sky. And you can see the footprint of it shown here on this map, looking very beautiful. We've actually made puzzles out of this map for some of us in the team. And we use this survey strategy that's wide and deep observations. So we have observations for that full footprint, but in a small area, we have very, very deep observations. And it's quite interesting that we use those to understand our data over the wide area. Now, the state-of-the-art telescope can do all kinds of other neat things. So if you've lost your car, it can help you out. So here's a picture of the Tesla Roadster that we observed. And also, if you're wondering if that shaking that you felt the night before was an earthquake, we can also help you out there. So on the left-hand side here is the image of the SpaceX Roadster. I think it was 3.5 million kilometers away at the time. And on the right-hand side are the observations from the night of an earthquake at the top of Cerro Tororo Mountain, which luckily I was not the one observing at that time. But really what we're after is the lensing data from these large telescopes. So the year 3 analysis that we just released results for spans the full footprint, so the full 1/8 of the night sky, but only uses the first 3 years of data. So there is still half of the data left in the can. So it goes, as you might have guessed, to half the depth that the eventual survey will go to, full area, half depth. And for the astronomy aficionados, that it has a mean redshift of about 0.6. Now, in the end, our catalog contained a whopping 100 million source galaxies. So that's 3 to 4 times the number of galaxies in area compared to the previous iteration of this survey and compared to the other surveys on the market. And that number really is staggering. So when I started my PhD, my advisor, Catherine Haymans, had just led the state-of-the-art analysis from a survey called CFHT Lens. And that was a very big deal at the time, but it had only measured 10 million galaxies. So you can see quite how much our data sets have grown in just this short amount of time, and that the field has developed very rapidly. Now, the Dark Energy Survey is a large team of scientists from all around the world, primarily in the US. And I think it kind of exemplified that science can no longer portray a lone man scribbling over a parchment. These groundbreaking experiments that will change our understanding of the universe require teamwork from a diverse set of people. So our international team has worked together to harness that data from the night sky and make our intricate measurements of the faraway galaxies and work through the enormous data set that we had. Now, Dark Energy Survey aren't the only people in the business. So I started my PhD at the right time because it was this very exciting era of having multiple surveys switch on the sky. Aside from DES, there's the ESO Kilo-Degree Survey, which is the footprint is shown in blue here. So I did my PhD, as you might have picked up from when Emma read the name of my thesis. I did my PhD as part of this primarily European team as a core member, and they are all fantastic, and I still work with them. Don't be fooled by the smaller area that you can see here. So area isn't everything in this game. So KIDS has particularly nice data in that it's 1,000 square degrees on the sky, so 1/5 of the size, but it has excellent wavelength coverage. And so this becomes really important for us when trying to understand the distances to our galaxies and being able to do that accurately and precisely. Then the HSC, the Hyper Supreme Camera Survey, has a much smaller area, but extremely deep, very beautiful data. And so really these 3 surveys are all competitive with each other, and our data sets are very different. And our teams work independently in doing our analysis blindly. I'll say more about that, not knowing the answer until we were done. And so the results that we found really are intriguing in that way. Now, here's why this field is particularly exciting at the moment. So let me set the scene for you as it stood before we released our DES year 3 results. So in this plot, you're looking at the S8 values on the x-axis. So that parameter, the amplitude of clustering, the amount and the clumpiness of structure in the universe. And we're comparing to the constrained value of S8 from the CMB measurement. So that yellow shaded band is what Planck's CMB, or the early universe, measured. The color data points are from all the different lensing surveys before DES year 3, so shown in red, blue, and green for the different surveys. And there's something pretty curious here. None of these measurements disagree with Planck CMB to any real significance. But our statistics tell us that the measurements should fluctuate around the model. But what we see is that lensing is consistently and persistently low. So our late time lensing measurements, the measurements from the late time universe, they're predicting a slightly discordant model compared to what the early universe dictates. So each measurement sits at about 1 to 3 sigma low compared to Planck CMB. And when you combine with results from clustering, so the top panel is lensing only and the bottom panel is lensing plus another probe galaxy clustering, then the tension that we see can get even more significant. Now this lowness exists from almost every weak lensing analysis to date. But lensing has always been challenging. The data is extremely hard to wrangle with. And so only now that we've really started to hone our methods, I think, is the evidence building up and people taking this more seriously. Now, why is this exciting? What does this mean? Well, there are three options for an explanation. Number one, I think the first one you might think is that the CME measurements are not quite right. But I'm even a little cautious to say that. These measurements are the gold standard of the field, and you would have to be very careful to claim that they are wrong. Now, the second option is that all the lensing surveys, all of the different teams were all missing something. But there are so many different results pointing to the same thing. And these teams have worked independently. So it's kind of racking up now the more and more data points that we get that they're doing something wrong. Now, the third exciting thing, which I think we're all secretly hoping for, is that we need some kind of new physics to fill the cracks. So should we expect that this model that describes the early universe can still describe our universe 13.8 billion years later? So it could be that we need some extension to Einstein's theory of gravity or some alteration to our model. Now, as lensing is a a relatively new field, the signal is very tiny to measure. And because it dares to threaten that gold standard CMB and this model that we're all quite proud of in some way, it's fair to say that our results are under scrutiny before we can go about saying that our model is broken or there's some evidence for different dark matter or different dark energy. We need to be very sure. And so after some years of work, DEF added a new measurement to that plot, and we were extremely careful knowing how powerful our data set was to do everything as best as we could. And so before I get to the result, I'll show you a little bit of what that process looked like. So this slide is overwhelming on purpose. It's to convey that it is a very hefty roadmap to deliver a validated and robust data set that enables precision cosmology or any of the countless analyses that benefit from the calibrated catalogs. So this is just a top level overview of this multifaceted process to convey that. So you're starting with images on the left-hand side, and then in blue, you have all of the different steps that you need to calibrate our data and to make the measurements to extract that lensing signal. And then you move to modeling in the orange, and finally to cosmology parameters or fits to our cosmological model on the right-hand side, so that S8 constraint. And each bubble has kept a team in DES busy for a couple of years, evidenced by the suite of papers that we published supporting our main results. Now, central to weak lensing analysis, as you might have taken away from the number of blue bubbles here, is a comprehensive understanding of the data. So on paper, this probe is extremely powerful, but in practice, it is increasingly difficult to extract the lensing signal from the images to the precision required by the statistical power. So specifically, it's getting hard to measure, calibrate, and validate the shares, the shapes that we measure, and also the redshifts, so the distances to the galaxies. Now, when I first started my PhD and I sat down with Catherine, measuring the shapes didn't really sound that hard. But this challenge of shape measurement is particularly one that we've worked on for a long time. So for those of you that are imagining 100 million Hubble-like images of galaxies that are very beautiful to look at, that's not what it's like. So weak lensing data isn't the picturesque spiral galaxies on the left, but more like the fuzzy blobs on the right-hand side. So you see that the light particles from a galaxy travel all the way across the universe, and they get gravitationally lensed by the large-scale structure, encoding the secrets of the universe that we're after, until they get to Earth. And the Earth's atmosphere will then smear and blur the image. Then that will happen some more in our telescope. The detectors will pixelate the image, and then there's noise. And so even that galaxy that you're seeing in the top right is a particularly nice one for weak lensing. Now, in the year 3 analysis, I coordinated the team at the time that measured and tried to understand the effects of the atmosphere and made sure that the shapes that we measured were validated and our catalog was robust. Then once we've measured the shapes, we need to estimate the distances to our galaxies or their redshifts. And this is really the most popular target for lensing skeptics. So with a student that I co-advised at Stanford, we led the work here. And I'll tell you why this aspect is so challenging and so scrutinized. Well, DES is a photometric survey. We just take images of our galaxy, and it would be much better if we could take beautiful spectra for each galaxy, like the black lines shown in this figure. Instead, we just have observations in a number of photometric bands or filters. And so with these limited observations, there's a huge amount of degeneracy between the type of the galaxy that you're looking at and how far away it is, or its redshift. So in this plot here, I can show you an example. There are 3 different galaxies, and they're all different types and different redshifts. So those are the different black lines. And if you had only RIZ observations of those galaxies, you would not be able to tell the difference between those redshifts with that limited information. So we built an entirely novel framework based on a machine learning technique of self-organizing maps, and we devised methods to account for all our sources of uncertainty. And in the end, this is an area where I think we really pushed the boundary of the methodology of the field. Now, just to add that this all gets more complicated thanks to an effect that we call blending. So as our telescopes get more powerful, we get deeper images, and that's great. But that means that we resolve further away galaxies than previously possible. And that means that our fields, our images, are now getting crowded. So some galaxy images are projected onto others. Now, how does one now measure the shape and the distances to all of the galaxies in this mess? So we use image simulations to detect and model the effects of blending, and then we can account for that in our analysis. And then finally, aside from the data, we need a theoretical model. So using our standard model of cosmology, we should be able to make predictions for what our measurements should look like. And computer simulations are really crucial here. And this was an area that Stanford plays a big role in. So any good school experiment would involve repetition, but of course we can't do that so easily when our experiment is the universe. So computer simulations bring us back to the lab setting where we can tweak our model and see what the universe looks like if we accounted for different galaxy processes or things like that. Finally, here are our cosmic share recleansing measurements. Now this plot there's a lot going on, but I'll just point you to the things that you should really take away. There are 2 different panels because there are 2 types of statistics, psi plus and psi minus, and there are a lot of different blocks because we have 4 redshift bins and you're doing each one with itself and with each other. But I want you to focus on the zoomed in panel. So up here for this 3-4 bin. Now, our data points are the black data points. The yellow shaded region is the size of the error bar in the previous version of DES analysis, so the year 1 analysis. And so this just really showed us quite how much statistical power we gained with the extra 2 years of data. And then the green line is our best fit model. And so the lower panels now are all the residuals. So the difference between our best fit model and our measurements. And I think what I take away when I look at that plot is quite how small those residuals are, or how good the model fits all of our data points. So this is one of the checks that we do. We make sure that the model is fitting the data well and describing the data well before we read off the results. Now, one thing that I want to emphasize as I go back to this picture is that all that time, which was 3 years, we had no idea where this data point would lie. So the most important point, I think, is that whichever way I preferred this turned out, it didn't matter. We do our entire analysis with obscured results. So we don't know whether our data will support a consistent story for our universe, with the standard model describing the early universe and the late universe, or if we'll find more hints for a need for new physics. So we make our measurements, we do our calibration, we tweak our model, all essentially with fake data. And then when we're sure we've done it right, we rerun the analysis with the real DES data. And so we're set up in this way that we can't bias ourselves to the right answer, either consciously or unconsciously. So as we really started finding a few months ago, this is what we found. So again, the blue and the red are from the other surveys, kids in HSC. The orange data point is from Planck CMB. And we found these green data points, so from lensing only above and then combined with clustering below. And in my opinion, these results were frustrating and tantalizing. So once again, like the other data, on its own, there is no compelling evidence that we need to deviate from our model. We sit at about 2 to 3 sigma. So that means a higher sigma value would mean that the discovery is less and less likely to be an accident or mistake or random chance. Now, what about when you consider the fact that all of the measurements are persistently low? Then it is clear that there is some kind of S8 tension, we call it, or some hints that there is something to keep digging at here. We combine our results with the clustering, as I said, and the tension stayed about the same. Now, I should warn that these different surveys are using different calibration techniques and different modeling choices. So it's not so trivial to just average the points in your head, combine them the way you would expect them to. But it is true that each survey has also been done blindly, the other data points, and making the best choices they could. So on some level, it is expected that when you combine them, we really will have a significant tension or significant deviation. So how do we learn more, and where do we go from here? With ongoing work, we are working the dark energy survey combined with the Kilo-Degree survey to do a joint analysis. So obviously this is one that I am particularly excited about, being one of the few people in both of those collaborations and getting them to work together, which hasn't been done before. So that's really exciting because we can combine the blue data points and the green data points properly here. And I think that will tell us whether there's more of a need for new physics or less of a need. And we have more data in the can. So DES year 3 was only half of the data. So we're currently working on the year 6 analysis, which I expect we'll finish in a couple of years. And the Kilo-Degree survey also has a final data set, the Kids Legacy data set, which should come out around the same timescale. But the story won't end there for us to figure out what this S8 tension is. It won't end with DES or with Kids or HSC, because really we're just the training ground for this bright future ahead. So as you stand on the top of Cerro Tololo in Chile, next to the Dark Energy Survey telescope, and you look one mountain over, there is Rubin Observatory. And so this is an experiment that I think everyone in our field is particularly excited about. And that's because next year, when it opens its eye, it'll be looking a new eye at the universe, and it will map the entire southern hemisphere every few nights for 10 years. So it will continuously stack up images until it makes essentially a movie of the sky, and it will be a total game changer, not just for our field, but for all different fields. So there's no doubt that the Rubin Observatory will be exciting. The year 1 data sets will contain more than 1 billion galaxies. So again, we're stepping up by an order of magnitude in the number of galaxies that we have. And that means that our work is cut out, because as we get more data, we need to hone our methods to make sure we can handle it and do our analysis robustly. And I included just at the bottom here some images while I was at Stanford and SLAC. They finalized the camera, they built the camera that will go on Rubin. And on the bottom right here is a picture of broccoli, which was one of the first images that they took. So the Rubin camera is ready to deliver high resolution images of your favorite vegetable until we start looking at the sky. Now, shortly after Rubin comes online, the Euclid telescope will be launched into space. And eventually after that, the NASA Nancy Grace Roman Space Telescope will launch. And so these telescopes that will launch into space will afford us better resolution in our images. So combining data sets, when we combine those data sets all together, the different sky and wavelength coverage, the image resolution, it helps us to understand our data better. So what I'm trying to say here is that the true power of all these data sets will really be when we're able to use them together. And I think that's when we'll have, I mean, it's already exciting, but that's when it'll be really exciting. And to end with, I'm curious to see how this S8 plot changes in the next years. Can we use the same measurements, the same model to describe measurements of the early universe and the late time universe? Or are we seeing the first cracks that is not the case? And with these incredible advancements in our technology and instruments and such exciting research prospects in the coming years, it's really hard to imagine how our field will look in a decade. But I hope you're as excited as I am to see where that goes. One thing I am sure about is that there will be many pieces of the puzzle still to solve. Thanks.
Alexandra, thank you so much for that wonderful talk and for sharing your work with us this afternoon. That was really fantastic. In the interest of time, I'm going to hand straight to Louise and give you the difficult task of picking one, maybe two questions from the list of questions I can see coming in. We won't have time for all of them. Over to you, Louise.
Okay, if we've only got time for a couple of questions, I'm going to go straight in with Amraditya Pradhan. Hello, I'm Amraditya, freshman studying computers and maths. I have a question related to Hubble deep fields. How do we distinguish the astrophysical jets and Hawking radiation from the redshifted star formation sites in the galaxy images? How does the graph differ in these cases?
That's a good question. So usually as a cosmologist, I never used to care about these jets or complex processes that are happening in galaxies. We can almost get away, or we used to be able to get away with treating them just as a number, these galaxies. They were just a shape and a distance, and we didn't really need to know very much more about them. Now, as we're getting such powerful data sets, I think we really are limited in that. We're seeing that we're limited in that. We need to understand the impact of AGNs on the shapes that we measure, on the distances that we measure, or on the model that we use. And so one topical area in our field is being able to use our small scale measurements. So I'm not sure if you noticed, but we end up throwing away most of our data, or at least about half of our data. So this blue shaded region, I didn't comment on this, is everything that we throw away, which is really quite a shame because we'd have a lot more power if we didn't throw them away. And that's because these complex galaxy processes make it extremely hard to model the measurements on these scales. So I think one area that I'm particularly interested in is better understanding the impact of these galaxy formation aspects on our measurements and on our models, so that we can actually use that data going forward.
Thank you. And just one more question then. Pedro Fanha, what makes the Planck 18 measurements the golden standard? And are there other measurements from the early universe?
That's a good question. So there are a few other experiments that came before, well, there's a couple that came before the Planck experiment, and now two ongoing CMB experiments. But the Planck really is the state of the art in precision. So if you look at their measurement of the power spectrum, which is what they measure best on the sky, so how much power there is at different scales. The error bars are extremely small, which is what I mean by extremely high precision. But more importantly, the fit is just beautiful. So it is hard to see how Planck, when I say gold standard, I mean it is hard to see how, given these measurements, that the model could wiggle. Or make room for these low S8 measurements that we're seeing in lensing. It is just, I guess, widely accepted that this experiment was really excellently done.
Thank you, Alexandra. I'm so sorry, we won't be able to take any more questions at the moment, and I'm going to pass straight back to Emma, but thank you, that was a great talk.
Thank you for having me.
Thank you, Louise, for that. And thanks again, Alexandra. So we're going to move straight on to our second speaker. And I'm really excited to introduce our next speaker, the award-winning author, Dava Sobel. So Dava Sobel is the author of several books about the history of astronomy, including the fantastic Longitude, Galileo's Daughter, The Planets, A More Perfect Heaven, and most recently, The Glass Universe. Dava's book, The Glass Universe, refers to the 500,000 glass slides that Henrietta Swan-Leavitt and other women used to document the northern and southern skies. The fantastic thing about Dava's work is that her stories combine real-life drama and historical scientific achievement into a really fascinating literary fusion. So I'm really excited to hear your talk this afternoon, Dava. Thank you. Dava's going to be speaking about the insight of Henrietta Swan-Leavitt adding depth to space. Over to you. Thank you.
Thank you for that most enthusiastic introduction. I really appreciate it. I am going to share my screen as soon as I get my presentation here. Okay. Slideshow. Can you all see the title slide all right?
Yes, we can. Thank you.
Okay, great. So the first thing is to thank you for inviting me to give this talk. I'm very excited to be here, even though I'm very far away in New York. But through the magic of Zoom, we are all together. And as you can see from the dates that limn the life of Henrietta Leavitt, we are approaching the centenary of her death, which is the occasion for this talk. I was invited to speak about her work because of this important anniversary, and to speak about her life, not just her death. This is the youngest image anyone knows of her, and it's undated. There's very little known about her early life. She was the daughter of a Congregationalist minister and was born in Lexington, Massachusetts. But then her father got an appointment at the church in Cambridge, Massachusetts, the other Cambridge, and the family moved there. And then he moved west to Ohio so that she attended the Oberlin Academy of Music for a while, and then Oberlin College. She began losing her hearing fairly young, and she went back to the East Coast to live with an uncle of hers in Cambridge, where she attended the Institution for the Collegiate Instruction of Women, and that later became Radcliffe College. And while she was at Radcliffe, she was very close geographically, just steps away from the Harvard College Observatory. And an astronomer from the observatory instructed the women in astronomy and took some of the really interested ones to the observatory to do some work. And she had studied astronomy as an undergraduate and had tremendous mathematical education and ability. So that greatly interested her. And the work that she did was completely based on photographs of the night sky. She did not use the telescope at all. So these treasured plates, 500,000 of which still exist at Harvard, were her version of looking up into the night sky. And the whole photography project was the work of the observatory director, Edward Pickering, who took over at a very young age. He was only 30 when he became director. And it was quite a controversial appointment because he was a physicist. He was not an astronomer. And his interest was not really in figuring out where things were and how they moved, but more generally the physics of the stars. And he began studying photometry, and he was very interested in photography and initiated this project to photograph the entire sky over a period of about a century. And that is what happened. So when he arrived at Harvard, there were already several women working at the observatory. These were the wives of the staff astronomers, the daughters of the former directors, and Pickering didn't have children of his own, but he immediately grasped the importance of these women to the work and how skilled they were. So he did not hesitate to hire other women. And the beauty part, which we can rue now, but these women would do the work of a man for 1/4 of a man's pay. And since the observatory really did not get any support from the university, any economizing was justified. Miss Levitt is not in this photograph, but the picture does make some things clear, how the women worked with the glass plates. So in the foreground, you can see someone has a wooden stand, and that's the stand that holds the plate. So it's in a frame, and the frame has some calibrations on it for measuring size. And then at the base, there's a mirror, and the mirror catches the light from the windows and directs it up through the plate for the best illumination. And she's using a magnifying glass and dictating to a partner who makes the notations, because it would be too hard to be looking closely and then turn to write things down. And in the background, so there's Pickering on one side of the room, but on the other side of the room, there's a woman looking through a modified microscope to examine a plate, and also dictating to a partner who makes the notes. Sorry, I keep losing there it is, to advance the slides. Okay. A lot of the work done involved looking at plates of spectra, but Ms. Levitt didn't do that. She was really assigned to photometry and to assessing the brightness of stars and establishing a sequence of comparison stars that would be useful in almost all situations, at least in the Northern Hemisphere. And since she was assessing magnitudes, she also became adept and expert at discovering variable stars. And there was tremendous interest in variable stars. Only a couple of hundred were known early in the 20th century, and she made numerous discoveries of them. And these were her tools for assessing magnitude. These were called fly spankers because they look like fly swatters. And her little joke was that these objects were too small to do a fly much damage. And you can see they're actually made from pieces of a glass plate. So they have stars on them for comparison. And these stars have been assigned magnitude from previous observations. So you can hold one of these over a current plate and make comparisons and judgments in that way. So here's a typical field. The images are mostly negatives, so the stars appear as teeny little black dots on a white background. And it was possible to make notations right on the plate, on the non-emulsion side, in colored ink. And many of the plates that Henrietta Leavitt worked on are now considered so historic that they're being withheld from the ongoing digitization project. It's been about 15 years that the National Science Foundation has been supporting a project to digitize all of these plates so that they are accessible and useful to current astronomers. This is one of her logbooks that she kept. This entire logbook has been digitized, and I've asked the technologically savvy people to put a link to the logbook on the event website, and you can page through the entire thing. And so these are her judgment. This is all about the Small Magellanic Cloud this particular logbook, and her judgments of comparison stars that she uses as a basis for following the variable stars. And this object, this is a paper photograph, print made of one of the plates that she has cut out and just taped into the logbook for reference. And she does that quite a lot. As you can see, her handwriting is extremely neat. Most of the other women didn't keep records quite this delicate. And the librarians just love this logbook. So to give you an idea of the size of the plate collection, this is the observatory building in the background here. And this brick structure had to be constructed just to hold the glass plates. And it was finished in 1893, right after Henrietta finished her studies at the collegiate institution. And so when she came to work, she would have been working in this building. There were about 30,000 plates when that building went up. And it wasn't just the space, it was the safety issue, because this building was brick. And the original observatory was a wooden structure. And Pickering had a mortal fear of fire. And in fact, trained a fire brigade. The observatory staff had to practice what to do in case of fire techniques, and they really got to use them at one point. By 1902, the building had to be doubled in size because the plates were amassing in the hundreds of thousands. And as precious as they were and as treasured, Pickering was willing to send them off to other astronomers who were studying a particular portion of the sky and might benefit from having a plate right at hand. And then, of course, astronomers were welcome to come to the observatory as visiting fellows and do research on site. So to get the whole sky, he had to send a scout to South America for a satellite observing station. And this is the first Mount Harvard in Peru, a temporary site that didn't have quite good enough weather or location to make it the permanent site. Oops. And this is how it looked when it really got rolling. So this is the Harvard station in Arequipa, Peru, in the lee of a volcano, but a volcano that was presumed to be extinct. And although only one of the buildings has a dome, several of the others actually do house telescopes. They just have a shed roof. And this is the director's residence. But this building on the inside housed this instrument specially designed and constructed for the site and the purpose of taking astronomical photographs. It's called the Bruce Telescope in honor of the woman who paid for it, Catherine Wolfe Bruce, a New York heiress. Pickering had to do a lot of fundraising to support the observatory. And he must have been extremely charming, because in addition to having all these women working for him, he had a couple of heiresses who were funding the projects. So the Bruce Telescope took very large format images. These are 14 inches by 11 inches, whereas a lot of the images were 8 by 10 or even considerably smaller than that. And you can imagine these very large glass plates getting packed up in Peru and going on a burro down to the port city, and then on a boat down the coast of Chile. There's no Panama Canal yet, up the Atlantic Ocean to Boston Harbor, and then to Miss Leavitt's desk. And there she began hunting through the image for variable stars. And she found 900 variable stars in this object alone, in the Small Magellanic Cloud. And this is the paper she wrote about her study of the two Magellanic Clouds. And I just want to call your attention to the byline. This paper was published in the Annals of the Observatory. They are formal publications that they tried to put out every year. And she, of course, got full credit for the work she had done. This was Pickering's practice, regular practice, always to allow the women to sign what they did. You will often hear a story about that claims that Pickering took credit for Miss Leavitt's work himself and issued it under his name. And I'm going to show you the source of that myth, but it isn't true. He definitely credited her. So this was a remarkable paper, remarkable to find that many variables. Some of them are extremely faint. She was looking at things down to 15th magnitude. And it was a very technical paper, about 12 pages of dense data presentation. And she did complete light curves for 9 of the variables. And she noticed, I think I have her exact phrase here, that it was noteworthy, it is worthy of notice that the brighter variables had the longer periods. So that's the first formulation of the period luminosity relation. Miss Leavitt was not well a lot of the time, and she would periodically leave Harvard for an illness or because she was needed at home by her family. And I think one of the reasons she didn't follow up her 1908 publication for 4 years was this pattern of having to interrupt her work. But in 1910, she was back at the observatory, and here she is. This is a meeting of the Astronomical and Astrophysical Society of America, what became the American Astronomical Society. And her more famous colleague, Williamina Fleming, standing right in front of her. This is Annie Jump Cannon, who is recognized as the author of the Harvard Stellar Classification System. Oh, be a fine girl, kiss me. That's all due to Miss Cannon. This is Pickering, front and center. He was president of the group. And down here is Solon Bailey. And he was the one who traveled to South America to find a spot that would be fitting for Southern Observatory. And he was the director of that station for many years. So here's part 2 of Miss Leavitt's great discoveries. And this time, it's not in the annals, it's Circular 173. The circulars were something Pickering introduced to get important news out quickly, rather than wait for the annals to be published and bound and distributed. These were brief news blasts that could be sent all over the world quickly and inexpensively, and astronomers could follow up on important discoveries. And so you see, there's no byline. But by this point, she has looked at some more stars, and now what she considered worthy of note, she deems remarkable. And at the bottom, so this is a 3-page circular, and at the bottom is Pickering's signature, because he signed all the circulars. They were a letter from him to the astronomical community. But if we go back to page 1, the first paragraph says, the following statement regarding the periods of 25 variable stars in the Small Magellanic Cloud has been prepared by Miss Leavitt. So he wasn't really taking credit for her work. And up on the top of page 2, in her words, she says that these additional stars conform to the same law as the ones she announced previously. So she used the term law 100 years before modern astronomers moved to turn the period luminosity relation into the Leavitt law. So in her study, since she was looking at the Small Magellanic Cloud, the whole point was that all of the stars were more or less the same distance from the Earth, and that was why she could make certain assumptions. But once she had published that data, other astronomers seized on it to actually determine the distance to the Small Magellanic Cloud by comparing the Cepheid variables that she had observed in it with other Cepheid variables in the Milky Way. And Einar Hertzsprung was the first one to come up with an actual distance to a deep space object. And his result was low, it was 30,000 light years. But at the time, that was farther away than anybody thought it would be possible to measure. So it was a stunning figure. And it was soon expanded to 80,000 light years by Henry Norris Russell. And it has grown since then to a current value of, I believe, 200,000 light years. Harlow Shapley took over the observatory after Pickering's death. Oh, and I should have mentioned, Pickering was twice honored by the Royal Astronomical Society with its gold medal. The first time in 1886 for the Harvard photometry, and then again in 1902 for his work on astronomical photography. So Shapley used the period luminosity relation to figure out the size of the Milky Way. And it was so gigantic. Here's the sun, and he thought the center of it was about here. So man was not such a big chicken. We were on the outskirts. And it was so big that he thought it had to be the entire universe. But then Edwin Hubble, also using Cepheid variables, showed that, in fact, the spiral nebulae that look as though they might be contained in the Milky Way are actually distant galaxies on a par with the Milky Way. And from Edwin Hubble, we went to the Hubble Telescope, And this is Wendy Friedman, who was head of a key project on determining the Hubble constant. And she was the one who first told me about Henrietta Leavitt and how the whole protocol of the key project depended on these discoveries made by a relatively unknown woman who had lived 100 years previously. And it's hard to emphasize how famous these women were in their own lifetimes. Miss Cannon on the left here was an honorary member of the Royal Astronomical Society and the first woman to receive an honorary degree from Oxford University. And Miss Leavitt was considered for a Nobel Prize in Physics. Unfortunately, the person who wanted to nominate her didn't realize that she had already died. It would have been the 1926 prize. And I see we are almost out of time, so I will just show you a final, one of my favorite images of the women. This is Henrietta Leavitt, and this is Annie Jump Cannon. Emma, I see your smiling face. Shall I stop there?
I could listen to you all evening, but thank you so much. That was just so interesting to hear all of that, and I'm looking forward to getting a copy of the book myself. So thank you, Dava. I'm going to hand to Louise and see if we have any questions or comments from our online audience.
Okay, thank you, Emma, and thank you very much, Dava. That was that was a really fascinating talk. I could have listened to that for a lot longer as well. So we've got a comment from Chris Lee, who's saying a key takeaway from your book for me was the importance of leadership. Pickering comes across as an exceptional and forward-thinking individual, and it was a shame his own centenary passed largely without notice.
I agree. I sometimes feel if I live long enough, I would like to write his biography because he was so important, and all of his material is at Harvard. They even have letters that he wrote to his mother as a child when he was away for the summer. And Alexandra's talk was so interesting, and she ended with that image of the jigsaw puzzle. Pickering was a great lover of jigsaw puzzles, and he used to do them. He used to turn the pieces face down so you could not see the picture. He would have been the one to solve the dark matter, the dark universe jigsaw puzzle.
Okay, that's really interesting. Is any of I just wanted to ask whether, I know you've done all this work's been done on the digitization, but are there ever any sort of anything that's exhibited for the public where they can actually go along and look at some of those plates, for example? Do you know?
Yes, a lot of the plates are available on the website. So the project is called DASH, Digital Access to a Sky Century at Harvard. And you can look at a lot of the plates there. You can also visit the plate stacks if you're ever in the States. And actually that building is still there. It's practically been swallowed by other structures, but it's there and the plates are there. And they will give you a magnifying loupe and put it on an electric light box and let you look at images.
Wow, that would be really great. Okay, I think I'm going to leave it there. Oh, hang on, we've got one more question. Are there 500,000 glass plates at risk of disposal when the digitization project is completed?
That is my worry. No one has mentioned that word yet, but one has to wonder.
Okay.
Maybe we'll all be volunteering to give them safe haven.
Yeah, it would be a shame, wouldn't it? So, okay, it seems like a sad note to end on, but I'm going to pass back to Emma, see if she can say something a bit more cheerful. But thank you very much, Dava. That was a really great.
Sorry to be down.
Yes, it's a real consideration, isn't it, with the digitization process? But how wonderful to be able to see them actually, if in the vicinity. I would love to see those. Dava, thank you so much for that wonderful talk. Thank you to both of our speakers this afternoon and for a really fantastic meeting, and thanks to all of you for joining us this afternoon. So finally this evening I would just like to give notice that there will be an additional A and G open meeting of the Society next Friday on the 19th of November 2021. So if you're able, do please come along to that meeting. Thanks again for joining us.